Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're going to discuss the plan of attack for this amazing section on the most powerful algorithm in artificial intelligence, which is A3C at the moment. So let's have a look. Today we'll talk about the following things. We'll start with the 3 A's of A3C. So we'll talk about what the abbreviation stands for and how we're going to deal with the 3 A's, and also we'll look at the actual article or the actual research paper that gave birth to A3C, the Google DeepMind research paper, and we'll have a quick look at it so that you're more comfortable navigating it in your free time. Plus, we will see exactly why the A3C is the cutting edge, most advanced algorithm on the planet for artificial intelligence at the moment, and why it's so important to have this in your arsenal. Next, we're going to talk about the first A of A3C, which is Actor-Critic. Well, A3C actually stands for Asynchronous Advantage Actor-Critic algorithm. And so we're going through the A's not in order, but we're going through them in an order that makes sense for us, that will help us in our intuitive understanding. Then we'll talk about the asynchronous element in the A3C algorithm. And then we'll talk about the advantage. And that's the tutorial where we'll put everything together and it all start making sense. So a quick word of caution that as you're going through these, you might notice that after the Actor-Critic and even after the synchronous tutorial, you will still not exactly have the full picture or full understanding of how this all ties in together. And that's totally okay, because all these 3 elements, they indeed work together and they require each other to function. So just power through it and get to the 3rd tutorial. And in the 3rd tutorial, the advantage tutorial, that's when it will all come together. And if at that point you still don't quite understand something, then you can just revise that specific tutorial, whether it's Actor-Critic or asynchronous or the advantage tutorial, to put all together. But basically, just don't get thrown off if after one of those 2 tutorials you still feel that you need some more information. That's because they all work together to come to one functioning A3C algorithm. That's in the advantage tutorial that all ties in together very nicely. And finally, we'll talk about some additions that you can add, or some additional modules and elements that you can add to the A3C algorithm. The thing is that there's different versions of the A3C algorithms, different modifications, and already through the first 4 tutorials in this section, we will see some modifications, and at the end we will add an extra one, the long short term memory, LSTM. Now here we won't go into a lot of detail on LSTMs. That's a topic for another course, but nevertheless you will get a overview of what LSTM is and how those structures or how those layers in neural networks work, so that you have a better understanding in preparation for the practical tutorials. But very important also, this will showcase how the A3C algorithm can be modified to suit certain purposes. So there we go. That's the plan for this section. Definitely it's going to be an exciting algorithm to look at, because it's the top algorithm at the moment in the world, and we're going to be developing an intuitive understanding, and then together with Adlan after this you're going to be coding it, which is very, very exciting. And I can't wait to see you on the first tutorial, and until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. In today's tutorial, we're taking our first step into the world of A3C. And as a first step, we're going to find out what this abbreviation stands for. So A3C stands for Asynchronous Advantage Actor-Critic Algorithm. This is an algorithm which was developed at Google DeepMind in 2016 by a group of researchers, and it's the cutting-edge algorithm for artificial intelligence to date. Now, it has multiple modifications, and we'll discuss that more in the course, especially in the practical tutorials, but nevertheless, this algorithm blows everything else, including deep convolutional Q-learning networks, out of the water, completely out of the water, and it is faster, it takes less time for training, and gets better results. So throughout this part of the course, we'll be referencing, and we have already referenced, but we'll be referencing even more, a paper, or the paper that was published that first introduced A3C. It's called Asynchronous Methods of Deep Reinforcement Learning by Vladimir Mnych and others from Google DeepMind. So I'm going to show you this paper now so that you have an introduction to it. So here is this paper. I wanted to show it to you so that you can get a feel for it and already get introduced to it a little bit. And of course, it is highly recommended to read through the paper and understand what exactly they're talking about. And you'll see that throughout the practical tutorials, Adlan will be taking you through certain parts of the paper, through certain paragraphs or sections, which will be relevant to what we'll be programming at that point in time. And what I wanted to point out here is, like, as you can see, it's a lot of research went into this, and there's a lot of references as well. But like a part that I really like is that at the end, the very end, they compare the different algorithms, compare the results. And this is what I wanted to point out here. So let's zoom in a little bit. So here, as you can see, they're even in Google DeepMind, they're training or they're evaluating the algorithms on games, just as we're doing in this course. So exactly the same principle, because games are a simulated environment or a small environment, a confined environment with certain rules, and they want to understand how well this artificial intelligence is doing in those games. And here we've got exactly all those games which you can find. A lot of them you can find on OpenAI Gym, and the games that we've been working with. So for instance, in this section, we're working with Breakout, so it's also here. And so you can see that for Breakout, they've got in bold, they've got the best algorithm highlighted. So DQN, that's the algorithm we've been working with. Then some other algorithms, and then here you've got A3C with an LSTM, long short-term memory. So that's the one we'll be implementing in this part of the course. We'll have A3C with an LSTM, which makes it even stronger. So as you can see, Breakout is the best result is achieved by A3C with LSTM. So that's the score, 766.8 compared to the others. And also you can see that for the most of them, so if we now take like a bigger picture view, you can see that most of the bold ones are actually in this last column. So yes, indeed, there are some games where other algorithms are performing better, but as you can see, DQN is actually not performing better in any of the games. But you can see that there are other algorithms perform better sometimes, but A3C LSTM performs the best in most cases. So you can see that this is bold, this one, these ones, this one, and so on. So you can see that A3C LSTM is a really powerful algorithm. It is indeed at the forefront of artificial intelligence, and that's exactly what we'll be implementing. So very exciting section ahead. Highly encourage you to go through this paper and get a feel for what we're going to be talking about, and then throughout this section and throughout the especially the practical side of the things, practical side of tutorials, we're going to be going through this in detail. We're actually going to be working with their pseudocode here, which is available, and we're going to be, so Adlan will show you how to implement that and how we're going to be working with that. And on that note, I hope you're going to enjoy this paper, and I look forward to seeing you next time. And until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the first part of A3C, the actor-critic part. So here we've got asynchronous advantage actor-critic algorithm, and we're going to be talking about that underlined actor-critic part. That's where we're going to start. You could technically start anywhere, but it just makes a lot more sense to start from actor-critic, because that way we'll have like a very consecutive explanation of, or intuitive understanding of what's going on. It's going to facilitate us better if we start surprisingly at the end of this abbreviation. All right, so far in this course, we've come up with deep convolutional Q-learning, which is illustrated over here. So we've got the computer seeing the pixels, so the actual image in pixels, not just a vector. So it's not cheating. It's actually seeing exactly what a human sees. It sees the monsters, it sees the health, it sees the parameters at the bottom, it sees the corridor, it sees the gun, it sees exactly the same thing as a human would see when playing this game. Then that image is passed through a convolutional layer, and then it's passed through a pooling layer, then it's flattened and goes into a neural network. And then at the output, we've got actions. As you remember, we've got those Q values. Then we apply a action selection policy to them. So for instance, we apply a softmax, and we find out which action we want to take. And so there's some exploration plus exploitation going on there, a combination of the two. So that is how deep convolutional Q-learning works. But now let's see what we're going to do with this. So for simplicity's sake, just so that it's easier for us to operate with this, because we're going to be adjusting this image and moving it around, we're going to replace the circles with squares, with these rectangular boxes, and we're also going to get rid of those lines in between, just change them to arrows. So this doesn't change the essence. This is just the representation on this chart. This is still, even this representation is still deep convolutional Q-learning. It's just going to be easier for us to modify it and show exactly what A3C is. So that's just how we're going to represent things from here. And what A3C does, or this specific part, so we're starting, remember, we're starting like step by step. We're starting with the actor-critic part. So we're going to see how we go from deep convolutional Q-learning to A3C step by step. And first step, we're going to introduce this actor-critic part over here. So we're going to talk about that. So the first thing that happens is this last bit, the output, is actually, we're just going to redraw it like this. So it's exactly the same output, exactly the same Q values, or exactly the same actions. So if you had 8 possible actions, you still have 8 possible actions. We're just going to put them at the top so they take up less space. So nothing has changed. So far this and this are exactly the same. But now this is where the actor-critic part comes in. We're going to have a second output. We're going to have, so the first one is a set of outputs, and here we're going to have a separate individual output. So technically we're going to be using our neural network. So once, and now, well, the image and everything, like the values go through the network from left to right. Over here, they don't just spit out one set of values, they spit up actually 2 sets. And so the top set, we already know what it is. It's the possible actions, but here we're actually going to have another extra value. So let's have a look at that. What is that value? So here we go. That's the top. So we just kind of like reduce the size of this illustration. The top output are the Q values, as we discussed previously, for the actions. So they're same thing, everything is same. But then now this bottom part, and the top part is actually called the actor. We're going to give it a name. That's the actor because that's the part where the agent chooses what it wants to do. So that it's like it's acting, it's as if it's performing on stage. And it'll make more sense once we have the second name up on the screen as well. And then the second output is just like one value, and that is V of S. So that is the value of the state. So if Q of S and A is the Q value of a certain action, and as you can see, that's why there's action 1, action 2, action 3, up to action 6, or however many actions there possibly are in that state. So in a given state S, what is the Q value of taking action A, action 2, action 1, action 2, and so on. Then here we're also using neural network to predict what is the value of the state we're actually in. And this part is called the critic. And so that's the intuitive, or the kind of not even full intuitive, that's just like the start of the intuition behind actor-critic, that there's 2 outputs now from the neural network, not just one. Before we just had that one output, which we now call the actor, but now we have 2 outputs, actor and critic. And there's going to be a dynamic between them, which we'll explore further. But for now, it's important to understand that we're predicting not just the Q values of the actions that the agent can take from this certain state, but we're also predicting the value of being in this current state using that same neural network. So that's the core of the first step into the actor-critic. And now we're going to need to talk about asynchronous, which we'll do in the next tutorial, in order to understand exactly what's going on between the actor-critic. And the final thing for today is that all of these Q values, as we know, that's also called policy. So in some literature, in some blogs, and some discussions you might find in the actor-critic, you might find the author talking about Q values on this side of the actor. In other literature and blog posts and discussions, you will find the author talking about the policy. So, and usually it's they use a Greek letter P for representing the policy, or it might just say policy of state S. So altogether, these are the policy of state S, because as we remember, the policy is if you put all the actions together, the possible actions, and then it's deciding which action to take. So these are going to be like the probabilities of taking each action. So that's the policy. So don't be thrown off if you see one or the other. They basically mean the same thing. So on one hand here, you've got the policy or the Q values. On the other hand, you've got the actual value of the state, and they're being predicted from the neural network. So that's the start of the actor critic. We'll continue with this in the next tutorial when we're talking about asynchronous. And I look forward to seeing you there. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're continuing our journey into the world of A3C, and we're talking about the asynchronous side of A3C. So there we have our abbreviation, Asynchronous Advantage Actor Critic, and today we're going to find out what asynchronous here stands for, what it means. And let's go back a step. Let's look at what we started this whole course with. We started with reinforcement learning and what it's all about, that the agent is in a certain state. They observe the state, they make certain decisions, they take actions in that state, and then the state is changed, so they get into a new state, plus they get a reward. So they get a reward for taking that action, or some sort of reward, which could be a penalty as well, and they end up in a new state. And based on that, now they take another action. Again, they get a reward, and end up in a new state, and they take another action, and so on. And so that is the basis behind all of reinforcement learning, and that's what we've been using in Q-learning, in deep Q-learning, in deep convolutional Q-learning, and that has allowed our agents to beat gradually more complex and more complex environments. But now we're going to introduce a better concept and even further, take this even to a further level. What A3C introduces through this asynchronous element is, instead of having one agent attack the environment, they have 3 agents, or whatever number of agents. So several agents attacking the same environment. And the key here is that why it's called asynchronous is because they're initialized differently. So their starting points are different. So for instance, as you'll see from practical tutorials, you set a random seed and you set it differently for each of the agents. And that way, because their starting points are different, they're going to first go through environments in different ways, and then they're going to explore in different ways. And then in the next iterations, they're also going to explore in different ways. And so, for instance, if you have 3 agents, all of a sudden you're getting triple the amount of experience. Instead of just one agent going through and exploring the environment and trying to understand how to operate in that environment, you now have 3 or however many of them going through that, getting this experience. And so so that each one of them is learning through this bigger experience. And apart from being just giving a broader range of experience, it also reduces the chances of one agent getting stuck in a local maximum. So for instance, if one agent finds like a way to beat the environment, which is not the most optimal, because if it deviates to the left or to the right from that solution that it found, it always gets more penalized. It might get stuck in that local maximum. It might just keep doing that, thinking that that's the optimal solution where it's actually not. Well, the likelihood of several agents getting stuck in that same local maximum decreases with the number of agents. So the probability of one agent getting stuck in a certain local maximum might be high, or might be a certain value. But the probability when you have 3 of them, of all 3 of them getting stuck in that local maximum, is much lower. And as long as they share experience between each other, they can help each other out. So if one of them gets stuck, for instance, it's stuck in a local maximum, just simply think that's the best one, that's the best solution all the time, and keeps doing that. Well, as long as it interacts with the other agents, so let's say this guy gets stuck in a local maximum, as long as it interacts with the other agents through the way we build our whole algorithm, A3C algorithm, they will help him out. They will give him knowledge that actually, no, hey, you should explore this, or he will be more likely to get out of that. And also overall, the environment will know that, hey, even though this is a great maximum, these other agents have seen better options, and we should keep exploring because they looks like they're better options. So in a very short, kind of rough, intuitive understanding, those are some of the advantages of having these asynchronous agents. First of all, you have more experience to choose from and to learn from. You could get to the solution faster, and generally speaking, there's a lesser chance of getting stuck in a certain local maximum. So let's see how this all plays out in this model that we've built so far. So as you remember, this is what we've gotten so far through the actor critic. And this is like where it all ties in. This is, so far, as you remember from the previous tutorial, we did introduce this, we had this already, even in deep convolutional Q learning. So we just named it actor now. But now we've introduced critic, but so far it doesn't really make sense. What's the point of having this critic and measuring the value of the state, or predicting the value of the state using the same neural networks, this same approach? But now this is the part where it's going to start making more sense. What we're going to do is we're going to replicate this, because now we have multiple agents. So with multiple agents, this is what it would look like. So the first way of imagining it is now we have these three things. Well, remember what we said about them sharing the experience between each other. So this is actually right now they're all independent. You have one playing the game, another one playing the game, another one playing the game. It's like launching your agent on 3 different computers. You put 3 different computers next to each other and you launch them, and that's great. Like, indeed, you'll get more experience, you'll get like more variety, especially if they're initialized different. So we're gonna assume from here that they're always initialized different. Even though we have the same picture here, we're going to know that they're actually initialized differently. So it's not going to be like identical training, identical learning from this game. And so even if you put 3 computers side by side and you launch them, yes, you're going to have more experience because you're going to have 3 agents playing. And also you're going to have a bigger variety of possible solutions. So that's true. But the problem is that they're not sharing that experience among each other. They're not learning from each other. So they don't have that synergy. They don't have the advantage or the extra power that they would get if they were cooperating. Like how if you have a team of people, they work better together than each one of them separately. So like in a team, here you got 1 + 1 + 1, it's 3. But in a team, 1 + 1 + 1 is not 3, it's like 33, because they leverage each other's strengths and mitigate each other's weaknesses. And same thing here. So if you put these 3 computers side by side, yes, you'll have more experience, more variety, and possibly someone will get to a better solution than the other one. That's great. But it'll be even better if they start sharing that experience. And how do they do that? Well, it's through this V that we calculated. So this V value that's the output of our network is actually like that. So they have this same V. So every time all these agents, they're contributing to the same critic. They don't have separate critics, they have a common critic. And that's the key of how the actor critic ties in with the synchronous. So there's one critic that's watching as they get experience. So how do we calculate the V? We calculate the V through, as you remember, we calculate the V through the values that we get. So the rewards that we get through the environment. And so as the agents explore their environment, they're predicting the V, plus they have the V that they can calculate. This is all ties back into what we've already discussed in the previous sections of this course. So they already have a V that they can predict, expect through the rewards that they know that exist in this maze, and that they've already explored. And as they explore them, of course, that value can change. But also they have the V this V is the output of the neural network. So as they're going through this, they're going to be adjusting their neural networks in order to better match that expected V. So basically, this is shared. The critic part is shared between the agents. And that is how they share the information between each other. That's how they are able to kind of see what's going on in the environment, share it with each other, and then use that, as we'll see further in the next part, in the advantage, use that in order to optimize how they're behaving in that environment. And the other thing to note here is, so this was A3C. This is like the core of A3C up to here. This is a version of A3C. But there's an actually even better implementation of this A3C, which you'll actually hear Adlan talk about in one of the first tutorials in the practical side of things. And what he'll be talking about is how the creator of PyTorch actually made an adjustment to one of the codes that was shared on GitHub, where he took all of these. As you can see right now, they have separate neural networks and only they share the V. That adjustment that was made was actually to take all of these neural networks and put them into one, take them and put them together. So ultimately, there's only one neural network here shared among the agents. So before each one of them had one neural network, which was shared for the actor and for the critic, one neural network shared for the actor, for the critic, one neural network shared for the actor, for the critic. Now they all have one neural network, which is shared for the actor, critic, actor, critic, actor, critic. And then the critic is here in common. So let's see. Let's move these pictures to the left over here. So make some space. And this is basically the architecture or the structure that we're going to be using in the practical tutorials. I know that like this may sound a bit overwhelming at this stage, but we've got one more A to talk about, which is the advantage, and there we'll see a bit better in action how this is going. So we'll talk about the intuition in action there. But generally speaking, this is what it is. There's one network which each of the agents use. So they share, basically what that means is that they share the weights. The weights of the network are shared between the agents. And when they update the whole network, not just their own network. And then they have outputs. They have like these actions for each agent. And then they have the critic that is shared, which is going to be monitoring. So I know all of this is kind of like there's a lot of stuff right now, but hopefully it's slowly coming together. At least the main takeaway from here is that the critic, because it's shared, that's how the agents are able to make sure that they're cooperating together in order to get to the result much faster. And then in the next tutorial, we'll see even further how all of this adds up, how all of this comes together. And for now, there's we would like to recommend you an additional reading. So this is a blog by Jaromir Janisch. It's called Let's Make an A3C Implementation. There's actually two parts, implementation and theory. There's the link, and it's very similar to what Adlan will be implementing in the practical side of the tutorial. So it's not specifically for this tutorial, not specifically just for this tutorial, but it's for this whole section. Encouragement there, some additional information, some additional insights there. And so that's why we're bringing it up here. But nevertheless, in the next tutorial, we're going to start pulling all of this together, everything we've discussed so far. And I look forward to seeing you next time. And until then, enjoy AI.